Here's a really interesting fluid mechanics question that was actually shown to me by one of my students. And it's actually a rather more advanced fluid mechanics, or it's related to a more advanced fluid mechanics topic that you do if you're maybe an engineering student in your second or even in your third year in some universities. So if you're interested in seeing anything similar to this on the channel or just any general fluid mechanics questions, please let me know in the comments. So here's what we have. We're dealing with a two-dimensional flow field, which is given to us by this vector. So this is technically a vector field that I'll call, I don't really like using U for the vector field, so I use sort of like lowercase v with an arrow on top, and the components of that vector is going to be x and minus y. Okay, so v is therefore equal to xi minus yj, right? So I and j are the unit vectors. So if we were to write this as a vector, which is what it is, this is how we can do that without necessarily using those brackets or the bracket notation. Okay, now in the first part of the question, we have to find and sketch the streamlines in the first quadrant. And the first quadrant is the same as, the first quadrant in trigonometry. That's where x and y are both positive. So if you think of the xy coordinate system like this, you have x, you have y. This is the first quadrant, right? This is the second quadrant, third, and fourth quadrants. So yeah, the first quadrant is here. So we have to sketch the streamlines, how they appear in this quarter of the plane. Right, so how do we do that? Well, we have to sketch the streamlines. So let's actually use this idea of the stream function, okay? So we know that in Cartesian coordinates, the stream function, the psi stream function, is given to us as follows. So the u component of the velocity, which means this, is going to be equal to the partial derivative of the stream function with respect to y, and v, or let's use this v, this is the vertical component of velocity, is minus d psi by dx. Okay, so we're going to use those to find out the stream function, and then we're going to plot them and sketch how the streamlines essentially look like. So we're dealing with two partial sort of differential equations, if you want, that we have to solve simultaneously in a way. So let's start with u equals d psi by dy. Now we know what u is. So u is the x component of the velocity vector, and the velocity vector is this. The x component is whatever I is multiplied with, which is x. So we have d psi by dy is just equal to x. And the other one is d psi by dx. So that's for the vertical velocity, right? That's equal to v, which is minus y. So I should probably put a minus here because we have a minus d psi by dx, which is equal to v, and that is minus y. We can cancel the minuses out, and the top equation is d psi by dy is x, and this one says d psi by dx is y. Okay, so far there's nothing extraordinary happening. And the other thing I'll do is I'll say that psi as a function of x and y. So now if I integrate this, right, with respect to y, x is going to be treated as a constant. So this will be x, y plus a function of x. Now, why is there a function of x here? So when you integrate, you usually end up with a constant. But we're integrating with respect to y, so there might as well be a function of x that we are not accounting for. So we must include that in here. And then if we integrate the second equation, we have psi of x and y is xy plus, and because we're integrating with respect to x, we might have, or we might end up with a function of y. Okay, and that's it. So those two are the same thing, right? So this one clearly has to equal to this one because they're the same stream function. And you can see that xy and xy are equal to each other, but then f of x and g of y also have to be equal to each other. So here's a question. When is a function of x equal to a function of y? Well, that's when both of them are constants. So when both of them are constants, then we have this equality that takes place. So f is equal to g and is equal to a constant. Now, here's what I'll do. I will not actually replace those with constants. Instead, I will say that psi is going to be equal to x times y. So in a way, I'm combining this constant by moving it to the other side with this constant, with the stream function itself, and this is what we will have. Okay, so this can be also rewritten as y equals psi over x, like that. And now we can plot how the stream function looks like, or how the streamlines look like. So we have x, we have y. Now, for each value of the stream function, we have a different streamline. So let's say if the stream function is 1, then y is 1 over x, which is, just the basic hyperbola, which looks like this. Right, now if this is 2, then y is 2 over x, which is something like that. And so on. So if psi is 3, then you have this. So each value of each constant value of psi corresponds to one streamline. And the other thing we would have to do as well is to say in which direction is the flow going. Well, we know the velocity. So we know that the velocity is positive along the x direction. So it must be like this. So it's positive in the x direction, it's negative in the y direction. So in the first quadrant, this is how the flow essentially looks like. And that's part A, or part 1. Okay, now let's have a look at 2. So plot the path of a particle released into the flow at 1, 1 and at t equals 0 seconds. And it says you should not have to make any new calculations, and they're asking why as well. Okay, so if we have to plot the path of the particle, then I would imagine we can plot the path of the particle in an xy coordinate system. And let's say this is part 2. And we know y is psi over x. So we also know that initially, so initially means that at time equals 0, x is equal to 1, and y is also equal to 1, like this. So that means we can actually use this initial condition to find what this psi value is. So in a way, you don't have to do any more calculations because you know the path is going to look like what's in part A, right? Because this is the y dependence on x, basically. So what we need to find is which of those streamlines is actually the streamline that we're considering. So to do that, we're going to replace y and x with 1 each. So we have 1 is equal to psi over 1, which means that the psi that we're looking at is equal to 1. So for the conditions, for the initial conditions that we have, so for our initial conditions, psi is equal to 1, therefore y is 1 over x. Which means that specifically for part 2 of the question, the answer is given to us by this streamline. So any streamline is a solution to the general equation, which is this, but for the particular initial condition that we have in part 2, it's only this streamline, which has a stream function equal to 1. That is the answer. Okay, now let's move on to part 3, and it's actually part 3 that's the more interesting bit here. Okay, so here's what we know. At time t equals 0, a marker dye is released into the flow along the three edges of the triangle with vertices, well, with those vertices. So let's maybe draw those points first of all. So this is part 3, and this is the xy coordinate system. Okay, so we have that the first point is here. Then we have another point which is 0, 1, so that's here. And we have another point which is this one. So this is point 1, 0, if you will. And this is the triangle basically. So if I use another color, maybe it's better. So this shape here is a triangle that we're considering. And it says, the question says that initially when we start our stopwatch, marker dye is released into the flow along the three edges of the triangle. Okay, and then we're asked to show that the diagonal line, so show that the diagonal line connecting 0, 1 to 1, 0 at t equals 0 evolves to form a straight line described by the curve. Okay, so at t equals 0, this shape, this is essentially the shape of the dye at time t equals 0. And then after a certain number of seconds, we're asked to show that this shape, the straight line, turns into a curve which has this other shape. Okay, so let's try to see how we can prove that. First of all, let's write the dependency between y and x at t equals 0. So at t equals 0, let's write this equation of the straight line. So this equation of the straight line is basically, if we call this x0, right, then this point here we'll have a coordinate y0. Okay, so y0 is just going to be equal to 1 minus x0, and you can actually check that easily by yourself, right? So this is this line here in that I'm outlining now. This is just a straight line with a negative gradient of -1 and a y-intercept of 1. Okay, and the equation is given to us by this. And then we have to figure out how this evolves over time. Now, from the previous part of the question, we know a couple of things. So we know that the velocity vector is xi minus, let me just double check, minus yj, like this. So knowing this, we can actually find out how the points on this line, right, because initially the dye is on this line, and we can find out where do they go, where do those points actually travel after a certain amount of time. And to do that, we're going to use the fact that we know the velocity vector or the velocity field related to those points which are sitting here. So this here is u, this here is v. So we have that u is equal to x and v is equal to minus y. So from here, we find that u is dx by dt, which is equal to x. Okay, so that gives us that dx by x is equal to dt, which means that ln of x is going to be equal to t plus a constant. Right, and in terms of v equals to minus y, we can do the same thing. So v is essentially dy by dt, which is equal to minus y. So dy by dt, or let's actually solve this straight away. We have dy by minus y, or let's leave the minus here like this. So ln of y is minus t plus c. Okay, so what do we then do with this? So let's take this one and let's write it as x equals something in terms of t. So that would be a constant times e to the power t. Right, so if you rearrange this, this is what you're going to get. If you rearrange this, what you're going to get is y is maybe this is C1 and this is C2, C2 e to the minus t. Okay, so the coordinate of x as time goes on, so the x coordinate of any of those particles after a certain amount of time is given by C1 e to the power t, and the y coordinate of the same particle after a certain amount of t is C2 e to the minus t. Now, the point here is to find what C1 and C2 actually is. So let's say that at time equals 0, we want that particle to sit on that straight line, right? So how do we put the condition that at time equals 0, that particle sits on the line? Well, we want that at time equals 0, x of 0 is going to be equal to x0, and y of 0 is going to be equal to y0, of course. So let's see what we get. We have x0 from the first is equal to c1 times e to the 0, which is just c1. So c1 is x0. And as you can imagine, we'll get something similar from the second equation. So y of 0, which is y0, is c2 e to the 0, which means c2 is y0. Okay, so let's rewrite those equations yet again. We have xt is x0 e to the t, and y of t is y0 e to the minus t, like this. Now, we also know what y0 is. So y0 is, we wrote it here, is 1 minus x0. So 1 minus x0 e to the minus t. Okay, because the initial y's and x's were described by that straight line. So that is e to the minus t minus x0 e to the minus t, which is sort of getting close to what we have to find, but it's not really the same thing. So we have to do an extra step, which is, if you look here, we can express y in terms of x, but what we have in our equation is we have y, which is good, but we don't have x by itself. Instead, we have x0, which is the initial x position of a particle. So to counter that, we're going to express x0 as x of t over e to the t from this first equation. So y of t is just going to be e to the minus t minus, and x0 is x of t over e to the t times e to the minus t, which is y of t equals e to the minus t minus x, and then this becomes e to the minus 2t. And that's basically it. And you can drop the as a function of t if you want, and that gives you the proof. So this is what we had to show. Okay, so in other words, those particles on this line, they're moving with a certain velocity, which depends on x, depends on y, and then after a certain amount of time, this straight line is not going to be straight anymore. It's going to be a curve that's going to be described by this right here. Okay, so we did this, and the last part of the question is compute the area enclosed within the Dye triangle at t equals 0 and later in time. Okay, so the area enclosed within the triangle at t equals 0, so at t equals 0, this shouldn't really be much of a problem, I presume, because you're just looking at a triangle, right? So the area of the triangle is going to be the base times height over 2, which is base is 1, height is 1, so it's 1 times 1 over 2, which is 1 over 2, whatever units you have squared. So to find the area after a certain amount of time, we also have to use the fact that, you know, the question tells us that x should be less than e to the power t. So we know that y is equal to e to the minus t minus x e to the minus 2t, where of course x is between those values. So how do we find the area under a curve? Of course we integrate, okay? So the area is going to be the integral of y dx, and the limits are the limits of x. So that's from 0 to e to the power t, and that is integral from 0 to e to the t of, and we have e to the minus t minus x e to the minus 2t dx, like this. Okay, now I know t is time, which changes, but obviously this is done at a certain time, which means that for those reasons, we treat t, time, as a constant when we're integrating with respect to space, to x, okay? So the area is therefore, or we can split this into integrals. I think it might be easier like this. So this is integral from 0 to e to the t, e to the minus t dx, minus, and then we have integral from 0 to e to the power t, x e to the minus 2t dx. Now the first integral is pretty simple. We just take this out because it's a constant, and then we have times x, integral, or the limits are from 0 to e to the t, minus, and then we can take this outside, and we end up with the integral from 0 to e to the t of x dx, which is e to the minus t times, this is going to be e to the t, minus e to the minus 2t times, and that's x squared over 2, from 0 to e to the power t. Right, so let's finish this up. We have area equals, let's try to work through this here. So this is going to be 1. That's pretty straightforward. Now this second term only exists when x is e to the t, right? Because when x is 0, then the whole term is 0. So that is 1 minus, we have e to the minus 2t times e to the minus, or e to the 2t rather, over 2, which is equal to 1 minus 1/2, which is 1/2. So that's it. That means basically that although this area will change, well, not the area won't change, the area will stay the same, but the shape of those lines will change with time, but they will change such that the total area captured, from here to here, like this area, will be always the same as the area that we started from, which is 1/2, which is an interesting result. So this does not depend on time. Why does it not depend on time? Because there's no t in this expression, it's just a number. Or everything that had to do with time got cancelled out. Okay, so again, this problem was the first two parts were relatively straightforward, because we just had to look at plotting the streamlines based on this stream function, which is based on the partial derivatives, or the velocities are basically the partial derivatives of the stream function. And then after we used some initial conditions, we were able to plot and see what the actual streamline looks like, which is this. And then in the second part, we had to see how the flow of some dye, which has this velocity or this velocity vector field, evolves over time. And then we found the area, which turned out to be constant with respect to time. And that's the end of the question.